So the product rule is a great way of evaluating the derivative of if we are differentiating the products of two or more functions. So remember, product means that we're multiplying functions together. So if I've got y equals f of x multiplied by g of x, then I can say that the derivative of y with respect to x equals the derivative of the first function, f dash x, multiplied by the second function, added on to the derivative of the second function multiplied by the first function. And in Lagrange notation, we say that y prime equals f prime g plus g prime f. Then if we want to look at it in Leibniz notation, if we've got y equals u dot v, then dy by dx, or the derivative of y with respect to x, is going to equal the derivative of the first function with respect to x, so du by dx, multiplied by the second function, added on to the derivative of the second function, so dv by dx, multiplied by u. So we're going to apply each of these notations in 3 examples. So the first example, we're going to use functional notation, and we're going to differentiate y equals x upon x plus 3 to the power of 5. So the first thing we want to do is we want to state that f of x is going to equal x, and g of x is going to equal x plus 3 to the power of 5. Now we want to differentiate and find the derivative of f with respect to x, which is going to be 1, and the derivative of g with respect to x, which is going to be 5 multiplied by x plus 3 to the power of 4, and then I would need to differentiate the inside of that bracket, and that's going to just be 1. So I don't need to do any further working out for that. So I want to work out what y dash x is. And y dash x is going to be the derivative of my first function multiplied by my second function, added on to the derivative of my second function multiplied by my first function. And now I need to substitute those in. So my f dash x is 1, and my g of x is x plus 3 to the power of 5. My g dash x is 5 upon x plus 3 to the power of 4, and I'm multiplying that by my f of x, which is x. Now I need to take out my highest common factor. So my highest common factor is the bracket x plus 3 to the power of 4. So I've got x plus 3 to the power of 4, and so if I take that from my first term, I'm going to be left with an x plus 3 inside my bracket. And if I take it from my second term, I'm going to be left with a 5x inside my bracket. So I'm going to have x plus 3 to the power of 4, and I'm going to have 6x plus 3 inside my bracket. And if I put it in ascending powers of x, I'm going to put my bracket 6x plus 3 first, and then x plus 3 to the power of 4, and that's my derivative of y with respect to x. So, in the second example, we're going to use Leibniz notation. So we're going to differentiate y equals 2x plus 1 to the power of 3 upon x minus 1 to the power of 4. So, this time I'm going to let u equal the first bracket, so 2x plus 1 to the power of 3. And I'm going to let v equal my x minus 1 to the power of 4. So I need to work out what du by dx is. So the derivative of u with respect to x is going to be 3 multiplied by 2x plus 1 to the power of 2, and then I've got to differentiate the inside of the bracket, and so it'll be multiplied by 2, and that will give me 6 upon 2x plus 1 all squared, and my dv by dx is going to be 4 multiplied by x minus 1 to the power of 3, and that would be multiplied by 1. So dy by dx is going to be the derivative of my first function, du by dx, multiplied by the second function, added on to the derivative of my second function, multiplied by my first function. And now we need to substitute in. So du by dx was 6 upon 2x plus 1 all squared, and v was x minus 1 to the power of 4. And I'm going to add that on to the derivative of my second function, which is 4 upon x minus 1 cubed. And I'm multiplying that by my first function, which was 2x plus 1 to the power of 3. Now I need to factorize. So the highest common number is 2. The highest common power of the 2x plus 1 bracket is 2x plus 1 squared. And the highest common power of my x minus 1 bracket is x minus 1 cubed. And then I want to take that factor out, so I'm going to end up with 3 multiplied by x minus 1. And I'm going to add that on to 4 multiplied by 2x plus 1. So now I need to expand those brackets in that final bracket. So I've got 2 upon 2x plus 1 all squared multiplied by x minus 1 cubed. And I've got 3x minus 3 plus 8x plus 4. And that gives me 2 upon 2x plus 1 all squared upon x minus 1 cubed upon 11x plus 1. And then I'm going to write it in ascending powers. So I'm going to have 2 upon 2x. No, I want my 11x in there because it's to the power of 1. So 11x plus 1, 2x plus 1 all squared upon x minus 1 cubed. And that's my value for dy by dx. So in the final example, I'm going to use Lagrange notation. So I want to say that my function f is x cubed and g is sine of 4x. So f prime is going to be 3x squared and g prime is going to be 4 cos 4x using my chain rule. So h prime is going to be f prime g plus g prime f. F prime was 3x squared, and I'm going to multiply that by g, which is sine 4x. And I'm going to add on g prime, which is 4 cos 4x. Multiply that by f, which was x cubed. I'm going to take out my highest common factor. This time it's x squared. And inside my bracket, I'm going to end up with 3 sine 4x plus 4x cos 4x. Now the final thing to note is that if we have a function that's a product of more than one function, so for example if we've got y equals f of x times g of x times h of x, or y equals fgh in Lagrange notation, then y prime is going to be equal to f prime g times h plus f times g prime times h plus f times g times h prime, and you can expand that for the product of as many functions as you possibly want.